My name is Jim. I'm a researcher at the Software Languages Lab at the Vrije Universiteit Brussel in Belgium. And today I'll be talking about my work improving the reactivity of pure operation-based CRDTs. I'm sure most of you already know what CRDTs are, but give me a quick recap. So basically, they're a family of replicated data structures where replicas can be updated independently and concurrently. Replicas can temporarily diverge in states, but will eventually converge when all replicas have received the same operations. Now, there are many different ways to implement CRDTs and different frameworks, but I will be focusing this presentation on operation-based CRDTs and more particularly the pure operation-based CRDT framework. This is a framework introduced by Boix et al. That propose a very nice way of implementing operation-based CRDTs. And it uses a log-based approach where every operation is stored in a log along with a timestamp. And the state of a CRDT can be computed by basically iterating over this log. Now, of course, this log will grow, so the framework uses causal redundancy and causal stability to ensure that this log is always as small as possible. And to do this, it makes use of a reliable causal broadcasting middleware, which provides causal ordering of operations and reliable delivery. And this middleware is used in a lot of different frameworks, different CRDT frameworks even, but there's one big problem that it actually introduces in the world of CRDTs, namely that it introduces a hampered reactivity. Let me explain what I mean with this exactly using an example. So let's say we have three nodes, A, B, and C, and these nodes are all replicas of a particular CRDT. All these nodes are connected to each other except for A and B, which are suffering from a network failure. Now imagine I apply an operation on replica C. This operation will probably be propagated to both A and B, no problem so far. Problems start when I apply an operation to replica B. This operation is propagated to replica C, but not to A because of the disconnection. Now if I at this point apply a new operation to replica C, this operation will be replicated to both A and B. However, it will be buffered by the reliable causal broadcasting middleware at replica A. And this is because if you look at the causal information flowing through the system, so between square brackets are vector clocks, you can see the middleware detects that there's a missing causal dependency, namely this operation Y from replica B. So basically, the middleware will then buffer this operation until this causal dependency has been arrived. So basically, once operation Y arrives, when the connection between A and B is restored, then operation Z will be applied. Now, of course, it might seem logical that you buffer these operations to respect these causal dependencies, but this is not always what you want, because in some cases, on the application level, on logical level, there might not be an actual relation between operation Y and Z. They may be totally unrelated, and in this case, even though they had a causal dependency, they were unneededly buffered. So basically the problem here is that even if operations Y and Z may be totally independent, because of the reliable causal broadcasting middleware, they will always be buffered if they're causally related. Now, this was a quite abstract example, so let me elaborate a bit more with an actual example on a pure operation-based Edwin set. So again, we're in the same situation. We have three replicas, A, B, and C, and there's this connection between A and B. And we have this sequence of operations that we apply. First, we apply some operations to replica C, this add X and this add Y. This is reflected on all replicas. There's no problems so far because there's no bad network connectivity with replica C. Then we apply an add Z on replica B. This is not reflected in replica A because of the disconnection. Finally, we perform a remove on replica C, and as explained earlier, this remove is now not reflected in A because A is waiting for the causal dependency at Z. Now, we can also implement this example as a classical observed removed set, which uses tombstones and not reliable causal broadcasting. And in that case, this implementation shows a higher reactivity, responsiveness to the operation that arrives, because it encodes this causal dependency in the form of tombstones, which are associated with elements that are added to the set. So basically the causal dependency is encoded on element level and not between all operations. So this means that the add sets and remove X, because they're based on different elements, do not affect each other. So of course this implementation, because I'm using tombstones, is really ad hoc and ugly, and it would be much nicer, really cool, if we could apply this same technique for pure operation based CRDTs. And this is exactly what we have done. Basically, we allowed developers to express these kind of associations by reifying the reliable causal broadcasting buffer. And basically, instead of only allowing the state to be constructed from the compacted operations and the log, we also allow them to take information from the reliable causal broadcasting buffer. And additionally, we'll allow information from this buffer to clean up operations, make redundant operations in the log. And we call this reified buffer the incomplete partial log. Incomplete because there are missing causal dependencies, and partial because we are having a partial causal order. Now, we implemented this as an extension to the pure operation-based CRDT framework. So here we have an example of the extended distributed algorithm. I will explain it so that everything will become a bit more clear. So initially we have this SI, which is the initial state, the empty log. And whenever we perform an operation, we will broadcast this operation to all replicas in the network. When an operation is received by a replica, it will be associated with a particular causal timestamp, which is added by the reliable causal broadcasting middleware. And then the pure operation-based CRDT framework will try to figure out what operations in the log or the new operation are redundant. And it does this using redundancy relations. So basically, in our case, the OR relation and the OR underscore relation. The OR relation checks if the new operation that arrives is redundant. If it's redundant, it will never be added to the state. And then it will check using the OR underscore if existing elements from the log are redundant by the new operation. So basically, if a new operation arrives and it makes elements redundant in the current log, they will be removed from the log. And OR extension is all about this on buffer hook below the deliver. It's very similar to the deliver, but it will be invoked whenever an operation is put in the buffer instead of delivered immediately. And we introduce a new redundancy relationship, or beta, which will check if elements from the log become redundant by this new buffered operation. And if so, they will be removed from the state, from the log. Then finally, we have the stable hook, which ensures causal stability and more, but that's less important now. Now, of course, this doesn't show the implementations of the OR underscore and OR beta methods. For that, we will look at the actual implementation of a CRDT. So here we have the implementations of an add win set and a remove win set. I'll only explain the add win set for brevity's sake. So you can see that the implementation of the OR redundancy, so the redundancy to check if the operation is immediately redundant, checks if it's a clear or remove. So this means that if an operation arrives in the set and it's a clear or remove, it will never be added to a set. Then the OR underscore relation checks if existing elements from the log are redundant. So here it says basically, if an existing element has a timestamp that precedes the new timestamp of the new operation, so as a causal predecessor to the new operation, and the new operation is a clear, or the arguments of the old operation in the log and the new operation are equal, then the old operation is redundant. So basically, if we receive a remove for element X, any add element Y, any add operation on element X that is already in the log, which is a causal predecessor to the new remove, will be removed from the log. Finally, we have the implementation of our OR beta, so the redundancy relation that we added to encode the relation between buffered operations and the log. And basically, it's exactly the same as the OR underscore. We check if the existing element in the log is a causal predecessor, and if the arguments are the same, or if the operation is a clear operation. And that's actually all we need to basically make this already much more reactive. In our serialization function to list, we also make use of the fact that we have this reified SB, the reified partial incomplete partial log, and we add it whenever we're serializing. We will use this information to make a more complete state. The remove win set is very similar, but I will not go into it. Actually have an implementation of this in our middleware Fleck, which I'm developing for my PhD, where I implement all my research artifacts in. And basically we have some snippets here on the slide which represent the code changes needed to implement these changes for that win set on code level, on CRDT level. And basically you can see that there's almost a one-on-one mapping between the proposed semantics and the code changes. So I will not go really into detail here. To quantify the reactivity of these changes, basically we performed an experiment where we have 3 replicas, A, B, and C again. And we instead of having a disconnection now between A and B, we introduce a latency of 5 seconds, meaning that operations between A and B will be delayed by 5 seconds. And in this experiment, every 250 milliseconds, a removal is performed on replica C. And we also add an item on replica B. And if you look at the graph, so the bottom line is time in seconds, and this one is log size, the log size of replica A. And you can see that the log size drops, of course, because we're removing items, but that there's the delay between if we implement the system using a non-reactive set, meaning a normal traditional add-win set, or a reactive set, meaning an extended add-win set. And you can see basically that you have this delay of 5 seconds because of course you're waiting for this causal dependency. But with a reactive improved set, this delay is removed and we are as reactive as possible. And with this I conclude my presentation. I introduced a way to improve the reactivity of pure operation-based CRDTs by reifying the reliable causal broadcasting buffer. Most modifications to CRDTs can be quite trivial and almost for free. We provide a formal specification on top of the pure operation-based CRDT framework and a proof of concept implementation in Fleck. For discussion and future work, I was thinking about maybe extending this to make items in the buffer itself immediately redundant, but this might not be beneficial and introduce complexities. If you have any questions, please go ahead. Thank you for listening.